Hello students, I hope you are fine and healthy. As you know, due to the recent developed circumstances, we are moving our instructions to the online, right? So here I am today to discuss about the experiment, vibrational rotational spectra of gases. Basically, we'll talk about the IR spectra of the gases. So before going to the discussions of the experiments, let me talk something about the background. So let me talk about the relationship between the molecular vibrations and the greenhouse effect. So as you know, the solar energy, so it has 46% visible and 45% IR, which is infrared, and 9% the UV visible light, right? And if you talk about the light which is absorbed, which is emitted to the space, actually 30% of light is reflected back to space, 50% is absorbed by Earth's surface, and the rest 20% is absorbed by the atmosphere, right? So the Earth can absorb light in the UV visible range, but it emits light in the infrared region, right? So this infrared region is the region where vibrational changes are absorbed actually. Some molecules, as you know, in the atmosphere, they can absorb infrared light, and they will increase the temperature. As you know, when they absorb the infrared light, the bonds of these molecules, they will vibrate, right? And then so this produces the heat, and the heat gets transferred to the another molecule, and it hits the another gas molecule. That's how we have the heated atmosphere. So this is called greenhouse effect, right? So we'll talk about what type of molecules will give the will absorb the infrared light. So basically, let's talk about the molecule which has like n atoms. The vibrational modes would be 3n-6 if it is non-linear, right? And if it is linear, the vibrational mode is equal to 3n-5, right? So let's talk about CO2, which is a linear molecule, as you know that, right? So if we have to find the vibrational modes, then 3 times the 3 atoms in the CO2 minus 5, that's equal to 4. So it has 4 vibrational modes. Wherever the water molecule, it has 3n-6 is equal to 3 vibrational modes, right? So for a molecule to be IR active, there should be a dipole moment, right? So dipole moment should change during the vibrational mode actually, right? So let's take 2 examples here, the CO2 and the water, right? So if you talk about asymmetric straits, so you can see this is asymmetric straits of the carbon dioxide, this is the asymmetric straits of the water molecule here, right? So this asymmetric straits is IR active. But if you talk about the symmetric straits, so you can see here the carbon dioxide and water, the symmetric straits, this is not IR active. Also, we have another vibration, which is you can see here for the carbon dioxide and for the water molecule, which is called a bending vibration. So this bending vibration is IR active. So basically, here, if you see here, the bending and the asymmetric straits, they are actually IR active, right? So from this we can we can figure out which of these straits is IR active, right? So as you know, the IR instrument, the reactive IR instrument, so it will detect the percentage of light which is which gets actually the incident light transmitted back to the instrument that the molecule doesn't absorb actually, right? So up to now we are talking about the molecule. So now if you talk about the quantum mechanics involved there, right? The energy of transition modes can be calculated. So to calculate the energy of transition state, the state must be quantized using some selection rules, right? So at room temperature actually, the lowest vibrational quantum number of a molecule can exist is V is equal to 0 and delta V is equal to plus minus 1, right? So the selection rule for rotational quantum number is represented by J, right? So is equal to delta J is equal to plus minus 1 and or like delta J is equal to 0. So for the condition that V is not equal to 0, right? So transition states can be now of three types: Q, P, and R. This is like they are called like actually the branches, Q, P, Q, R branches, right? So Q branch, this is when you have delta J is equal to 0. So P branch, this is when delta J is equal to minus 1, and R branch, this is when you have delta J is equal to plus 1, right? So this is about quantum mechanics. But if you talk about, if you just want to figure out where are your Q branches, P branches, and R branches in the actual spectrum, right? So here I have written here. So Q branch, this is found in the center of the percentage transmission, right? Intensity. The P branch is found in the lower wave number, and then the R branch is found in the higher wave number. So let's talk about the actual experiment that we are doing today. Okay, and then so what we are trying to do is we'll use the carbon dioxide, right? So in different atmospheric pressures. So for example, like different pressures, what I am saying, first you can take the 1 atmospheric pressure, which is almost like 103 kilopascal, right? So we'll take the pressure of the carbon dioxide lower than that, maybe maybe 90 kilopascal and also like 80 kilopascal, and see the difference in the spectrum, right? So here we have the FTIR instrument,